Welcome to techthetalks.com. We are still advancing with our mighty branch, organic chemistry, and I wish that each and everyone would really try to understand organic, because organic we are basically studying about carbon and its properties, but subdivided into a number of homologous series simply to make it easy. Since studying it in bits makes it a bit easy. We now advance to introduction of organic chemistry. Introduction of organic chemistry. Introduction of organic chemistry. We need to first understand what organic chemistry is, because organic, like we said, is all about the study of the chemistry of carbon and the study of the chemistry of carbon and its derivatives, or with itself or with other compounds. Like carbon would have reacted with nitrogen, which is a possibility. To study with hydrogen carbonates. If we can critically analyze those reactions, those elements, those properties of carbon with those other elements, then we would say we are studying about organic chemistry. Now, we can advance and look at the properties of organic compounds. Properties of organic compounds. It is important that we understand the clear-cut difference between organic compounds and inorganic compounds, because I said at a later time I'll be coming in to teach about inorganic. But what makes inorganic different from organic is that inorganic we study about a variety of elements of the periodic table. But here, out of the very many elements of the periodic table, we so much dwell on carbon as the center of organic chemistry. Why do we have so much study about the carbon and the organic chemistry? The reason is this carbon, this organic chemistry, forms one of the properties is that it forms complex structures, and there are very many of them. There are very many. Yes, organic chemistry has got very complex structures and are really very many. I want to give an example. When we look at this compound, it is a structure in organic chemistry, very, very important reagent. That is just one structure. It is quite big enough, and it is very rare to find a compound which is as big as that in a branch like in organic chemistry. So I want to say this is one example or a property of organic compounds. They are very big, that's complex, and again they are quite very many. So this compound is called 2,4-dinitrophenyl hydrazine. 2,4-dinitrophenyl hydrazine, or a common name we can call it Brady's reagent. Can also call it Brady's reagent. So that is one of the characteristics or properties of organic compounds, that they form very complex structures. Then another property another property is that these organic compounds are usually insoluble in water. Now, to understand that they are insoluble in water, we need to know that why are they insoluble in water? Number one, water itself is a polar solvent. Polar solvent means there is a displacement of the dipoles. When you look at water, that is the chemical formula of water, has got this oxygen atom, and this oxygen atom is more electronegative than the hydrogen atom. So there is always a tendency that the water, the oxygen, since it is more electronegative than the hydrogen, it tends to withdraw bonding electrons towards itself, even without notifying hydrogen that I'm going to take the bonding electrons. So that tendency of withdrawing electrons towards itself makes it acquire a partial negative charge and leaving hydrogen with a partial positive charge. So why is oxygen able to do that? Because it is highly electronegative. It is more electronegative than the hydrogen atom. So the formation of the partial positive and partial negative causes it to be called polar. In other words, formation of the dipoles. So water is a polar solvent. But then when we look at organic compounds, since we have said that they majorly contain carbon, this carbon, the electronegativity difference between carbon and hydrogen is almost the same. There's no difference in the electronegativity value of carbon and the electronegativity value of hydrogen. Although it is there, but it's too small. So we can say there is no electronegativity difference. And since there is no electronegativity difference, then there is no formation of dipoles. You look at carbon and carbon, then look at the hydrogen surrounding it. There is no electronegativity difference. And when there is no electronegativity difference, then you cannot form dipoles. So the two can't react, because if there were positive charges, positive dipoles on this organic compound, then the positive charges or dipoles would be attracted by the negative dipoles of water. These negative positives, dipoles of the water molecule, would attract the negatives from the organic compound. And since that is not a possibility, then organic compounds are normally insoluble in water. They are normally insoluble in water. Now, the last one, it may not be the last, but the most important is about the electronic configuration of carbon. Remember, we are studying about organic chemistry, and the center of organic chemistry is carbon. If we could study properly the clear-cut differences between the properties of carbon, then we'll easily understand the organic chemistry. When we look at electronic configuration of carbon, first of all, carbon is element number 6 in the periodic table, and its electronic configuration in O level, we write it as 2 to A. We write it as 2 to 4. That totals up to 6. But for our main concern now here at advanced level, we look at carbon to have electronic configuration of 1s2, 2s2, then 2p2. Now, this 1, 2, 2 represents a shell number, or you can say this one is shell equals to number 1. The whole of this is n equals to number 2. So that means the carbon has 2 shells, and therefore belongs to period 2 of the periodic table. Now, by the virtue that the whole of this is outermost shell, then we expect all those electrons in the outermost shell to participate normally in chemical bonding. But when we look at this innermost NS orbital, that is 2s2. If I draw the orbital, we are going to fill in one electron like this, and then pairing comes in later. Now, these two electrons are already paired in that 2s orbital. Because they're already paired, they don't participate in chemical bonding. Now, look at the outermost, this one. This 2p, the 2p orbital. This p orbital is further subdivided. The 2p subshell is further subdivided into 3 orbitals. That is the 2p x. This one is the 2p y, and this one is the 2p z. But then we are seeing, realize that in the 2p orbital, we are having a total number of 2 electrons, meaning that we are having a total number of 2 electrons, and the p subshell has got 3 orbitals. So when we are filling in electrons in this orbital, we fill in one by one, then pairing comes in later. We cannot fill 2 electrons in one orbital, then we leave others without electrons. So I've filled in one in the 2px. So I can say the 2px orbital has 1 electron. Then we go to the 2py, which is also having 1 electron. So these orbitals are already taken up. We don't have any other electron to fill the gap in the 2pz orbital. So therefore we can say that these electrons in the 2p orbital are unpaired. And when they are unpaired, then they participate in chemical reactions. Now, but these ones in the inner 2s orbital are already paired. And since they're already paired, they don't participate in chemical reactions. So when we study this scenario, somebody could easily think that carbon exhibits a valence of 4. Yeah, because you look at 2 unpaired electrons, then these are unpaired, don't participate in chemical bonding. So somebody can be mistaken to think like carbon exhibits a valence of 2, which is not right. Now, but what happens is, under ground state or ordinary conditions, carbon does not participate in chemical reactions unless forced or unless drastic conditions are taken, and that can be achieved if carbon is supplied with some energy. So when we supply it with some energy, we can say carbon will undergo excitation. So I'd reached a point of looking at, does carbon has a valence of 2? Does carbon has a valence of 4? So now, under ground state, carbon has a valence of 2. But at ground state, carbon does not react. So if we want it to react, then we have to supply it with some energy. And that energy causes excitation like this. We can first look at ground state carbon. At ground state, carbon has atomic number 6. It is 1s2, 2s2, 2p2. But when it goes to excited state, this excited state is achieved after carbon has absorbed enough energy to allow it to react. You can supply it with energy through heating it. Yes, through heating it, excited state. So we shall have carbon 6, 1s2, 2s2, this is supposed to be 2s1, this is 2s, 2ps, this is 2p3. In other words, when you supply it with energy, the orbital, 2s orbital, doesn't absorb the energy, but the energy is absorbed by the electrons in the orbital. If we supply electrons this carbon at excited state, the electrons in the 2s orbital, this one which had unshared electrons, or the one which had a lone pair, absorbs sufficient amount of energy. And once it absorbs sufficient amount of energy, the electrons in that orbital can no longer afford being in that orbital. Remember, electrons only occupy orbitals which are equal in energies. Once an electron acquires much more energy than the orbital can withstand, then it is promoted to a higher orbital with a greater energy. So we are saying that when we supply energy to the carbon, the electrons in the 2s orbital acquire more energy than the s orbital can hold. So therefore, one of them is promoted so that it goes to an orbital which is higher in energy. Remember, the p orbital has more energy than the s orbital. So therefore, it is promoted. In other words, when we draw our orbitals here, we can say we have, this is now, this is 2s2, this is the 2p2. Now, once carbon has acquired or